So this talk is about combinatorial polytope theory. So let me start by telling you what I mean by a polytope. So in this talk, at least a polytope will be the convex hull of finitely many points. Okay, so you have a finite set of points, say in R to the D, and you take the convex hull, and such a polytope can always be described as the intersection of finitely many hull spaces when this intersection is bounded. Okay, if you take only one hull space, then it's not a polytope. And these are examples of polytopes. This is probably the simplest example. It's called a simplex. Okay, you take some finally independent points, you take the convex hull and you get a simplex, or more like famous family of polytopes are the Platonic solids. So these 5 polytopes in R3. And the way I drew them, there's some symmetry. This is given by polarity. It's a simple geometric operation that will send this octahedron to the cube. And what it does, it sends vertices, which are the faces of dimension 0, to facets, which are the faces of codimension 1. So here you see this octahedron has 6 vertices, and this cube has 6 facets. Okay. And here we have 8 facets, and here we will have 8 vertices. And in this case, in general, you send faces of dimension k to faces of dimension d minus 1 minus k. So if you do the numbers, you'll see that edges go to edges, and that's why they have the same number of edges. Okay. And the simplex here in the middle, it's self-polar. It will appear often this word simplicial. Simplicial polytopes are those where all the faces which are not the polytope itself are simplices, like this one, and this one. Simplicial polytopes are polar to simple polytopes. Let me just say the definition of being simple is that it's polar, it's simplicial. In some sense, most polytopes are simplicial, because if you take a random set of points for anything, any reasonable like definition of random, and you take the convex hull, then you'll get a simplicial polytope, right? It's like when you perturb slightly the vertices, you won't have 4 points in a plane. So you will never have faces which have more than 3 vertices, for example, in R3. Okay, but in the same sense, most polytopes are simple, because if you take a random set of hull spaces and you take the intersection of a random set of hull spaces, that if you do some small perturbation, you always get a simple polytope. And this is important in some sense because we are counting, and it always depends on how you look at the problem to say what's most, right? And I will mostly be centered in things that are vertex centered and not facet centered. Okay. And if you want to do the other picture, you just have to polarize. Okay, so this is combinatorial. So these were polytopes, and let me tell you what's combinatorial about them. And that's the phase structure. So let me define a phase as the intersection of the polytope with a hyperplane that does not cut the polytope, that does not go through the interior of the polytope. Okay, so we'll have vertices when this intersection is of dimension 0, edges when this intersection is of dimension 1, and in this case, we're a 3-dimensional polytope, we'll have facets when the intersection is of dimension 2. If the hyperplane doesn't intersect the polytope at all, then we'll have the empty set, and I would like to say that this is a phase. And I also want to say, which is not compatible with my definition, but I also want to think in general that the whole polytope is a phase. And the reason why I want to present it this way is that if I order the phases now by inclusion, this partially ordered set is a lattice. Okay, and that's what we call the phase lattice of the polytope. And this is what's combinatorial about the polytopes for me. When I look at the polytope, I don't only see a geometric object. I see a combinatorial object because I only see its phase lattice. Okay, and this is again important when you are counting, because of course there are infinitely many polytopes. Okay, any subset of points give you a polytope when you take the convex hull, but I want to consider them up to some equivalence relation, and my equivalence relation is having the same phase lattice. Is this clear enough? Okay, So we learned in Alberto's talk that it's good to give some historical remarks. So I'll follow the pattern, except that I'm very bad at this. So I decided to cheat and to take one of the sources. Okay, so this is Grunbaum's book on convex polytopes. If you go to the Google Ngram search and you look for convex polytope, you see that this started moving when this book was published. Okay, it's like the seminal book on combinatorial polytope theory. Like now there are many more books on the topic, but this is really the first one for modern combinatorial polytope theory. And if you start at the preface, it starts like telling you slightly the story of combinatorial polytope theory. And he says that polytopes have been with us since antiquity. I mean, actually, like if you go to Euclid's Elements, the last book was just the construction of these Platonic solids. So it's something that really goes back. And then he talks about Euler's famous theorem. This is the one that says if you have a three-dimensional polytope and you count the vertices plus the number of facets, you get the number of edges plus 2. And which is considered to be the first landmark of combinatorial polytope theory. Okay? So this is my like summary of this preface. It starts with antiquity, and then we have Euler's relation. And then there were like some work. He mentions like Cauchy, Steiner, Sylvester, Cayley, Mobius, Kirkman, Schläfli, and Teit. And says, however, about the turn of the century, there was a decline in the interest of convex polytopes. And he gives two causes, and they suit very well the first one suits very well my talk, because the first cause is that there was this problem enumerating the combinatorial types of convex polytopes, which has very hard, even in dimension 3. And people decided that actually working on combinatorial polytope theory was hopelessly hard, so they gave up. Okay. The second reason was that other mathematicians didn't see this as a serious topic in general. Okay, and I'm happy that this has changed, and this has one of the proofs is that we have a new combinatorics group at UB, and I'm very happy about this. That this is like the first time that like nowadays combinatorics is not anymore seen as a let's say lesser part of mathematics. Okay. So we continue with this history, and like it starts, the people start working, and then they just hit this problem, which is counting polytopes, and they just give up. Okay, so let me do a parenthesis. I will continue with Grunbaum's book later, but let me do a parenthesis at counting polytopes, so that we are clear on what's the problem that we want to talk about. So I already mentioned this, okay? We will want to count up to some equivalence relation, and this equivalence relation will be the combinatorial type, okay? So we want to say that two polytopes are equivalent if they have the same phase lattice. So like, well, in the plane, which is where I can do the pictures, this is not extremely interesting, okay? There are only polygons. So I want to say that all quadrilaterals are equivalent and they are not equivalent to a pentagon. This is somehow has some extra hardness, which are symmetries, which again, you don't see them in the polygons, but when you are counting, you will have to take into account the symmetries of the phase lattice if you want to count things to be different. So actually, it's much easier, or at least like you separate like two problems, which one is considering symmetry and the other one is considering counting polytopes, when what you count instead is labeled combinatorial types. And this is when you have the vertices of your polytope, you give them numbers, okay? Let's say you have n vertices, you give them n vertices. So for me, these two polytopes have the same labeled combinatorial type, because if you look at the faces, here I have an H12, and here I have an H12, and here I have an H23, an H23, and so on. But I will consider this one to be different from this combinatorial type, because here I don't have the H12, okay? So during the whole talk, when I'm talking about counting polytopes, I'm actually talking about counting labeled polytopes, labeled combinatorial types. In general, you have a factor of n factorial from one to the other. But if you want to really look like it's not exactly n factorial, and if you want to mod out these, then it's a lot of work, okay? Because you have to understand the symmetries of the polytopes. Most polytopes don't have any, but nevertheless. So anyway, this is what we're going to do. So let's start counting, okay? So in dimension 0, there's only one polytope, okay, which is a vertex, a point. It has one vertex. In dimension 1, there's only one polytope, which is a segment, which has two vertices. And in dimension 2, if you look at the unlabeled combinatorial type, you have one for any n to me. So just if I forget, n is always the number of vertices, and d is the dimension. Okay, so for every n that is at least 3, you have one polygon with n sides. And if you want to count with my rules, you have to take labeling into account. Okay, so actually you have one way of labeling a triangle. You have 3 ways of labeling a square. And in general, you have n minus 1 factorial divided by 2 ways of labeling a polygon. Okay, and this is because actually polygons do have symmetries. Okay? You have the dihedral group, but in general, in higher dimensions, you won't have these symmetries. Okay, and let me do a parenthesis here, which is strongly related to counting polytopes, but it's not counting polytopes, which is counting triangulations. So a triangulation will be a subdivision, in this case, of a polygon into triangles. And I want to count triangulations is just for the sake of these parentheses. The rules are different. So now the polygon, the vertices are fixed, and we are only looking at the way of subdividing it. And we can count how many ways are there of triangulating a triangle. There's 1, 2 ways of triangulating a square, 5 ways of triangulating the pentagon, 14 ways of triangulating the hexagon, and so on. And I wanted to do this parenthesis because these are the Catalan numbers. So, but there's nothing Catalan about them. They are called Catalan because some Belgian guy called Eugene Catalan studied them. He did not invent them. It seems like the first people who really like found actually the formula for the Catalan numbers was Euler and Ziegler. There's some nice pieces of let's say I don't know what historic history of maths that tell you actually on the one hand who found these Catalan numbers, which was not Catalan, and then somebody also tried to see why do we call them the Catalan numbers. So exactly who was the first person who like started like saying these are this number are the Catalan numbers. Apart, it's like, you know, Eulerian numbers. It's not enough information because Euler did too many things. So that's why I think the Catalan numbers stick. So anyway, the Catalan number, the nth Catalan number, is the number of ways of triangulating a labeled n plus 2 gon. And I'll start with the segment. I also say that they have one way of triangulating the segment. And since I have a slightly more, like the privilege of being senior is that I have like 15 more minutes. I have the time to give you a proof. So let's count the Catalan numbers. And here's the proof. You take your polygon, and I want to count the triangulations. And you know, the edge n plus 1 will be attached to a triangle that will go to some vertex. And then we'll have like 2 independent triangulations, one of the left side and one of the right side. Okay, and I'll do that for every possible neighbor of this edge. And this gives this recursive formula for the Catalan numbers. Okay, you have to sum for every I the triangulations of what you have here times the triangulations of what you have here. And now you can take the generating function. So this is a formal power series where the coefficient of z to the n is the nth Catalan number. And this recursive function translates into this equation for the generating function, which you can solve. And you get this nice formula, which is one of the formulas handwritten in the wall of the CRM. And now you can go check if this one is the one that has the mistake or not. Okay, so let's continue with the Grunbaum. Okay, so we are at the moment where polytopes are not interesting anymore in general, except for some people that are either like maybe on the boundary of polytope theory, like Alexandrov, Coxeter, Minkowski, with one notable exception, which is Ernst Steinitz. Okay, so he did a lot of work on polytope theory during this period, and in particular, he made a theorem which is nowadays known as Steinitz's theorem. So let me tell you about Steinitz's theorem. And what he says is, if you want to understand a three-dimensional polytope, you can understand it combinatorially the following way. So you can consider the graph, which is made by the vertices and the edges of your three polytope. Okay, so take any polytope. So you take a polytope and you consider the vertices of your polytope as the vertices of your graph and the edges of the polytope as the edges of your graph. And you have a graph and you want to characterize those graphs. Okay, and he says, actually, it's relatively easy. The graph of a polytope will be a planar graph, meaning that you can draw it into the plane. To see it, just put a light bulb inside your polytope. It will cast a shadow on the sphere, and then you can project the sphere to the plane. So you have just drawn the graph of your polytope onto the plane. And it will be three connected, meaning that when you leave two vertices out, you can still connect any two vertices of the graph. And this is not hard to prove. So this direction is actually quite easy to prove the down direction. And what he did is to prove the converse, which is that if you have any three connected planar graph, then you have a convex polytope with that graph. If you join this theorem that characterizes graphs of polytopes with the fact that if you know the graph of a polytope, of a three-dimensional polytope, then you know the whole phase lattice. This is only for three-dimensional polytopes, but if you know the graph of a three-dimensional polytope, you can tell who is a phase because that's actually non-disconnecting circles of the graph. Just again, not hard to prove. What this tells you is that actually, like somehow the combinatorial types of three-dimensional polytopes is something very combinatorial. I'm not talking about geometry. I only have to enumerate planar graphs that are three connected if I want to enumerate three-dimensional polytopes. I don't have to worry whether there are coordinates that make something convex with this structure. Okay, Steinitz did that for us, and this is like actually I want to like highlight this. This is what makes a huge difference between three-dimensional polytope theory and higher dimensional polytope theory. Okay, this is no longer true in high dimensions. In particular, for example, if you have anything that looks like a polytope, but it's not convex at all, but like you say topologically, let's say you have a simplicial complex of dimension 2 that is homeomorphic to a sphere, then you can realize that as the boundary of a convex three-dimensional polytope. Okay, so which means that every simplicial 2 sphere is polytope. Again, these are things that will no longer be true in higher dimensions. And thanks to this theorem, now enumerating three-dimensional polytopes, which is actually the very hard problem that Grunbaum alluded to, this is essentially solved nowadays. It's very combinatorial because you only need to enumerate graphs with certain properties. Okay, and I mean, to tell you how precise this is already in 1962. I mean, there's some technicalities which are again always the problem is symmetries. So you want to kill symmetries, but if you root your polytope so that you're killing some symmetries and you're only looking at simplicial polytopes, that he's not even giving an asymptotic approximation. This is a precise formula. This is an exact number, okay, for any. So this problem is, so this is the simplicial case. If you don't do the simplicial phase. There's again a precise formula. We know anything, okay, except how to deal with the symmetries, which are very, very rare. But if you want the exact number, you need to know how these symmetries play. So that's the only thing that people are still working and have not managed to solve. But otherwise, like, you know, like everything is known asymptotically about polytopes in dimension 3. And what happens in dimension 4 is that we have a phenomenon that will kill all these approaches and all the hopes of solving this, which is universality. So to present this, I need to introduce the concept of realization space. So now what I want you to imagine is I choose my combinatorial type, my preferred combinatorial type, say the cube. And now I want all the geometric polytopes with the same combinatorics, okay? So to parameterize this, I can just take the coordinates of the vertices. If the convex hull have the phase lattice that I want, then, so, you know, like if I have a polytope with n vertices, then in dimension D, I can make a matrix of D times n with the coordinates of my polytope, take the convex hull. If this has the combinatorial type I want, I put it in my set, okay? And this is the realization space, which is a subset of R to the n to the times D. This makes sense? Okay, so this is, you know, it's the opposite of moduli spaces in the sense that this is only one equivalence class of the moduli space, okay? It's the one equivalence class of this combinatorial equivalence that I'm talking. So this is the realization space. And what happens, so realization spaces of three-dimensional polytopes are nice. If you have two things that look like octahedra, you will be able to continuously go from one to the other, and through the path you only will have octahedra, okay? This is no longer true in dimension 4 and larger. Actually, quite the opposite is true. Like imagine your worst nightmare, you know, like the ugliest thing you can imagine in the like, and this is like, well, there are some big words, but imagine you're like any semi-algebraic set. There will be one polytope that encodes this semi-algebraic set in a sense that the realization space will be as ugly as your favorite semi-algebraic set. But semi-algebraic sets are quite flexible. So for particular, they can be disconnected or they can be anything. So that means that these realization spaces can be as ugly as any semi-algebraic set, which is uglier than what you want, okay? In particular, it's very hard to decide whether a semi-algebraic set is empty or not, okay? And this tells you that it's very hard to decide whether a polytope exists or not. And what I mean by that is, like, if I don't want to go back to the slides, but imagine you go to one of the first slides where there was a phase lattice, okay? So I give you the problem, I give you the phase lattice and you have to decide, is this the phase lattice of a polytope or not? Okay, so this is the problem. And there are some simple checks you can do, okay? I don't know, like every phase of dimension D has to have at least D plus 1 vertices. But this problem is hard. It's hopelessly hard. You will not be able to solve it, okay? It's at least NP hard. It's actually exists R complete, which is to be equivalent to being able to solve systems of polynomial inequalities, okay? So we will not be able to decide whether a phase lattice is the phase lattice of a polytope or not. So there's like no hope for combinatorial enumeration, okay? Anything that we can count, if you are able to count, you are able to decide whether it exists, right? And I'm telling you that this is hard. So all what we can hope for is some approximation, which may be better or worse, but like exact enumeration is out of the game. Okay. You have questions? I'm going on with Grunbaum. So we were left with despair. I mean, well, universality, Grunbaum didn't talk about it because it was not discovered at that time. But we were at the time where polytopes were not interesting. Okay. And then something happens, and this something are computers. Okay, and like people needed things that you can compute on, and polytopes actually turned out to be very useful for computers. And actually, all combinatorics had a regrowth. Okay, and in particular for polytopes was the linear optimization was what was the big motivation, because you could sell your research saying that you were doing linear optimization, or just you were doing linear optimization, and that gave you interesting problems on polytopes. Okay, and that was what was the reason for the rebirth of combinatorial polytope theory. And he mentions as one of the focal points the phenomenon of neighborly polytopes. So let me tell you what a neighborly polytope is. So yeah, I didn't read everything, but he talks about neighborly polytopes and the upper bound conjecture. So let me tell you about this. So neighborly polytopes. And I won't present you the upper bound conjecture, but the upper bound theorem. It was proved some years later. Actually, the story is, he mentions the upper bound conjecture by Motzkin. What we have of Motzkin is an abstract of a talk he gave, where he doesn't present a conjecture, but a statement. Okay, he says this. We never saw a proof by Motzkin, but he also makes other statements that later turned out to be false. So I think we can assume that he did not have a proof. He was just so that's why it's called the upper bound conjecture. And now for that we have a proof. So the problem here, and now you have to go beyond your three-dimensional mental picture. So let's say I give you a polytope with n vertices. Okay, what's the largest number of edges you can hope for? I want you to give me an upper bound for the number of edges of, let's say, of a four-dimensional polytope. Edges is one-dimensional, faces. I give you an upper bound, which is, well, best you can hope, every pair of vertices are joined by an edge, right? So the upper bound, the trivial upper bound is n choose 2, okay? And let's continue. What's the most you can hope for the number of two-dimensional faces? Where if you are lucky, you have triangles, and every three vertices will make you a triangle, so you'll have n choose 3, okay? And the question is, well, the first is, can you do that? And if you can have, imagine you can have the n choose 2 many edges. How far can you push it? Can you do it for all dimensions? Well, the answer is you can do it up to dimension n half. Okay, so a polytope is called neighborly if up to dimension n half you have all possible k-dimensional faces. So for every k up to d halves, you have that any subset of size k is a face. So these are neighborly polytopes, and these actually, so they clearly maximize the number of faces in low dimensions, but they actually do also, they all have the same number of faces, and they also maximize for higher dimensions. And if you're curious, the maximal number of faces is of order n to the d halves, okay, maximal number of facets. Okay, and this is the upper bound theorem that tells you what is the maximal number of facets or of faces in every dimension that a polytope in dimension d with n vertices can have. If you want to construct one such polytope that has the maximal number of faces, which is neighborly, you can do it this way. So take what we know as the moment curve, which is the curve t squared, t to the 3, t to the 4, etc., and take n points in this curve, and you take the convex hull, you'll get a polytope, which will always have the same combinatorial type. It's called a cyclic polytope, and it has the property of being neighborly and of maximizing the number of faces, okay? And what Motzkin said was that this polytope, the cyclic polytope, would maximize the number of faces in every dimension, which is true. And then he said, and this is the only polytope that has this property, which is false. There are many more polytopes that have the property of being neighborly. Okay. Let me, actually, it was, so why did I put two names here? Well, McMullen proved this, the upper bound conjecture in 1970, so shortly after Grunbaum's book. But actually, something much stronger is true, and that was proved by Stanley, which is that this is also true if you only take something which is topological. So a simplicial sphere that has, so a simplicial complex homeomorphic to a sphere that has n vertices, and it's a d-1 sphere. It also has this number of faces maximum. Okay, so if you want to have a simplicial complex that is homeomorphic to a sphere and that has n vertices, you will not have more than n to the d halves many simplices. And this is also a very important result, not only because of the result, but because he used commutative algebra and algebraic geometry, and this is the birth of combinatorial commutative algebra. So now that this is like a very important field, eventually this led to Junhu's Fields Medal, but it all goes back to this paper by Stanley. Okay. Corollary. We can do our first bound because we know that we don't have more than a certain number of facets. That's called M. And I have n vertices. How many combinatorial types do I have? Well, every combinatorial type is given by how do I spread the vertices into the facets. Okay, so I have m facet. Let each facet choose its d vertices. Okay, and this gives you one trivial upper bound for the number of combinatorial types, which is of order n to the d halves. Okay, we said this was valid for spheres, so this is a valid upper bound for the number of simplicial spheres. Okay, this was first observed by Calais, but it's really a trivial upper bound. Okay, so here it's saying this is the number of facets, and every facet will be a subset of d vertices. So this is the number of possible subsets of d vertices. So here is every facet, it choose its subset of the vertices. So this is a very coarse upper bound. Is it so coarse? And the answer is no. Okay, it's actually not so far from the truth. I mean, okay, when you're working with such big numbers, this is not so far from the truth. It's huge. Okay, so this is 2 to the n to the d halves. And this is n to the n to the d halves. But the difference between these two numbers, it's huge. Okay, it's a log n in the exponent, but yet, I mean, it's reasonably small because it's only a log n in the exponent. Okay, but I mean, these things sometimes when you work on this, you lose perspective. You say, you know, like, well, like every tiny improvement, you have to produce many more. You know, like. So how do you do this? You do a construction for many simplicial spheres. Okay, if you want to do some more, but if you want to improve, like you have to like do many more. And like a small improvement, they won't appear in these numbers. Okay, in order of magnitudes. So this is what we know for simplicial spheres. There's two dates because like we have like one for odd dimension and one for even dimension. There was like something about this rounded down. And we know that we don't have more polytopes than spheres because every polytope, like if we stay in the simplicial case, every polytope is a simplicial sphere, the boundary. But of course, we don't know if it's far from this or not. Okay. And it's far, okay, so this is not so many polytopes. So there was a first paper that the title tells you everything I need to tell you in this section, which is there are asymptotically far fewer polytopes than we thought, okay? Then this was slightly improved later, and this is what I'm citing. And this is an upper bound for the number of d-dimensional polytopes with n vertices, okay? Which is, I like to draw it this way, n factorial to the d squared. Okay, this is very far from what we have here, which is 2 to the n to the 2 to the n to the d halves. Okay, so this is 2 to the n to the d halves. This is 2 to the n log n. Okay, when d grows, this is very, very far. Of course, in dimension 3 not. We just said that every simplicial sphere is polytopic. But in general, most spheres in high dimension are not polytopic. Okay, and this is something funny. Well, funny. Like we know that if you take any random sphere, it will not be polytopic. Just the numbers don't like the polytopic are. But we know very, very few spheres that we can prove that they are not polytopic. Okay, it's very hard to decide whether a sphere comes from a polytope or not. So actually, we have very few examples that are handcrafted that show that this sphere is not polytopic. Even though we know if we take one at random, it will never be polytopic. And let me tell you how you prove this. And you use this theorem by Milner and Thom that's bounding the number of sign patterns of polynomials. So you take some polynomials, okay, and now every point will evaluate, so real polynomials will evaluate either positive, negative, or 0 on that polynomial. So that's what I tried to describe with this small picture, okay? And this theorem bounds the number of different sign patterns that will appear, okay? So this point, for example, is negative on the first. Actually, this is wrong. I think this is positive. So sorry for the mistake. So this point should be positive for the first polynomial, negative for the second, and positive for the third one. So you have number of sign patterns, and this theorem bounds this number of sign patterns. If I remember correctly, the way of proving this is you bound the sum of the Betti numbers. This bounds the number of connected components. And so actually, first you do it for those that have no zeros. This bounds the number of connected components, and this bounds the number of sign patterns without zeros. And how we connect these to polytopes, and I think, forget maybe, there's a lot of information in this slide. Let's just look at this picture. And what I want to tell you with this picture is that if you know the orientation of every simplex spanned by your points, so here I have a triangles, and I want to know if they are positively oriented or negatively oriented with respect to the order, whatever order you have chosen. What I want to say is that if you know this information, you can tell whether something is in the boundary or not. And this is the picture I want to, like if I have this edge, which is in the boundary, now if I do look at the orientation of this triangle with respect to this order, is the same as the orientation of this triangle with respect to this order, and the same as the orientation of this triangle with respect to this order. So all these orientation match, and this tells me that this edge is on the boundary. Whereas here, if I do this one, and this one, if I look at the orientation, it's opposite from this one, and this one. And this tells me that this edge is not on the boundary because it has points at both sides. Of course, orientations, this is just looking at the sign of a determinant. So now here are the polynomial systems I was looking at the previous slide. So this, I can make a polynomial system given by these determinants, and the sign patterns is, again, very coarse upper bound for the number of polytopes. Okay, and if you plug in the numbers, you get an upper bound of n factorial to the d squared plus O plus something, which is 2 to the n of that. And this is like the end of Grunbaum's introduction. Almost, he says that, well, now research into combinatorial study of complex polytope has growth at an astonishing rate. And nowadays, I would dare to say it's an established field and with a very active community. Then, so this doesn't end the introduction. Then he says what he will teach you in his book, but I didn't copy that. So this ends the introduction, and let's start with the talk. So I want to tell you about something that happened after Grunbaum, and I was involved with respect to this problem. And so I just sketch an upper bound for the number of combinatorial types of polytopes. And I want to tell you my work on the lower bounds on the number of combinatorial types of polytopes. And this is the story of the problem almost. So there was a first big bound of order 2 to the n log n. So these are, in some sense, this solves the problem because the upper bound was also 2 to the n log n, okay, by Schemmer. And something which is amazing is that there's the word neighborly here. So, you know, Motzkin conjecture, there's only one neighborly polytope, which is the cyclic polytope. And it turns out that the largest family of polytopes that we know, they are all neighborly. Okay, so this was wrong by far. Okay, there's 2 to the n log n many neighborly polytopes. And then this was improved for simplicial polytopes. So we lose this property of being neighborly to n factorial to the d4th by Alon. So see that once you've settled this asymptotic dependence, what you're looking here is essentially what's the constant in front of n log n. This is a constant that depends on d. And if you were looking at this game, now Schemmer proved a 1/2 and Alon proved a d/2. And this topic was, let's say, dead for 30 years until I did my PhD thesis, where I slightly improved Alon's bound to d/2. I want to highlight that, I mean, it's very tiny improvement, but it's a lot of work because there are very large numbers. Okay, so you really need to produce many polytopes. And also, I won the word neighborly here. Again, like I have to confess, this is not what I was looking for when I was working on this. Actually, like somebody gave me a problem where they needed to have a neighborly polytope with certain properties, and I tried to construct it, so I couldn't, and so I worked very hard on making a construction that was very flexible to construct new neighborly polytopes. I never managed to find the one that has the right property, so I had to go to my backup plan, was just count how many I constructed, and it turned out there were more than nobody ever constructed before. Later, I proved that the polytope with that property didn't exist. So, anyway, but this is not the recent work I wanted to tell you about. It's something which is more recent, just last year with Francisco Santos and Eva Philippe, who is my PhD student until next month when she's defending, where we managed to further improve this bound to n factorial to the d-2 without the neighborly polytopes, okay? And what we do is we take the polytopes that we had here and we prove that all of them have many triangulations. So we go back to this Catalan combinatorics. So when I tell you about the triangulation in higher dimensions, I mean a subdivision into simplices. A special family of triangulations are those that are regular, which is you take your polytope and you lift it into one dimension higher, you lift it as you want, and you look from below, and you'll see some subdivision, and this is a triangulation. This, like if the heights are arbitrary enough, then this is a triangulation. For example, all triangulations of polygons arise this way, but not all triangulations arise this way. Actually, most triangulations are not regular. For example, one nice exercise is to prove that this cannot be done this way. And I still have like 2 minutes, so let me still give a hint of what I did. The relation between regular triangulations and polytopes is that if you have something lifted like this and you add a point at infinity, then you have the combinatorics of a polytope in one dimension higher. And we go back to the proof, okay, of the Catalan numbers, but I want to think about it in a slightly different way. So what happens here is, imagine you have two vertices which are very close. Then every triangulation, you can think of it as a triangulation of the polytope you get when you merge the two points. And you have to decide how to divide the triangles that you have here. Some will go to the vertex W and some will go to the vertex V. Okay, and you have to be able to decide which go to which side. And this works also in higher dimensions. If you have two vertices that are close enough, and this is like close enough has a very precise meaning, then every triangulation like this one, you can understand it by taking a triangulation of the two vertices that are merged. So this is a triangulation of this. So see the two vertices there are merged here. And now in my triangulation, there are some that will go with the red vertex and some that will go with the green vertex. I don't want to give more details, especially because I'm soon over time. Essentially, so what we do is we are actually prove that if everything goes to the red vertex is a regular triangulation, if everything goes to the green vertex is a regular triangulation, and you can continuously go from one to the other, being always regular. And you know you have as many as like small flips that happen in this path from one to the other. And since my polytopes were neighborly and there were a lot of faces, you have to flip through a lot of faces, and this it gives you the viability. And this is the proof. And something very interesting on what happens here with respect to previous constructions is that previous constructions we had control. I can give you the face here. I know that there are many if I go through this continuous path, but I don't know who this continuous path is. I don't know anything. So I don't know. I know I've constructed many polytopes. Well, we have constructed many polytopes, but I don't know who they are. And let me finish here. Thanks you for your attention.